lesson in two-dimensional motion, and we're going to talk about unit vectors today. Okay, so we're going to be talking about vectors in 3 dimensions. There's 3 main ways that you can describe a position in space. We're used to the Cartesian coordinate, where we have the x-axis, the y-axis, and the z-axis. This is the conventional way of displaying the 3-dimensional Cartesian axis. And then another way that's described on here is the spherical coordinate system, where you have a vector, and the first component is the length of the vector, or sometimes it's called the r vector. Think of it as radius. Then there's the angle that the vector sweeps in the xy plane, and that's phi, and that's called the azimuthal angle. And then the last description is the angle from, this is called the zenith, and sometimes it's called the altitude angle, and that's described by theta. So 3 components to make up the spherical coordinates. The third description, or the third coordinate system, is called the cylindrical coordinates. The xy plane has radius and angle, and then the z-axis stays the same. We will be mostly concerned with working in Cartesian coordinates and converting to polar coordinates, which is just xy plane with radius and angle. Now, unit vectors. They're quantities that specify direction only. The unit vector has a magnitude of exactly 1. That's what we mean by unit. And they're described, or they're notated by the little hat, or some people call it the roof. I call it the hat. I hat, j hat, k hat. Okay, I hat is a vector that has a length of 1 and points in the positive x direction. J hat has a length of 1 and it points in the positive y direction. K hat has a length of 1, points in the positive z direction. If you were to find the magnitude of I hat plus j hat plus k hat, what do you think the magnitude would be? Well, I think it's probably 1. Why else wouldn't we call it a unit vector? Okay, let's move on to some more vector shenanigans here. Okay, so here's a pictorial of what the unit vectors look like on a Cartesian axis. Now, why do we have unit vectors? Instead of using magnitudes and directions, which are in the polar coordinate system or sometimes cylindrical coordinate system, we represent our vectors by their components, which are actually scalar quantities, multiplied by their unit vectors. So multiplying a scalar by a vector by a scalar is just multiplying that vector's length by the amount of the scalar. So if you're multiplying the component by 1, you just end up with a component, and the unit vector gives it direction. Okay, so here we have an example of a displacement of 30 meters in the x direction, a displacement of 60 meters in the negative y direction, added to a displacement of 40 meters in the positive z direction. And that gives us a displacement of, and this is in unit vector notation, it describes both, it describes the vector completely. Okay, 30I hat minus 60J hat plus 40K hat meters. And then there's another notation method that's used, linear algebra. That's how we actually do algebra with vectors. And the notation is in square brackets, 30 comma negative 60 comma 40 meters, and that describes the same vector. I use both notations. Throughout the course of instruction, so you need to be familiar with both notations because they are used somewhat interchangeably. Now, to add these vectors together using unit vector notation, you simply add all the I components together, all the j components together, and all the k components together. After addition through the component method, we didn't call them the I, j, and k components. We just call it the x component, the y component, and the z component. So we're really not doing a whole lot different. It's just an easy way of notating a vector. Okay, so here's a problem for us, and we're going to add two vectors, a and b together, and that'll give us our resultant, which is c in this case. So vector a is 3.00i plus 7.5j. Vector b is negative 5.2i plus 2.4j. So we're going to add those together. So a plus b. So we take the I component of each one, add it together. So we have 3 plus a negative 5.2, which gives us negative 2.2 I hat. And then we do the j's. And it's 7.5j plus 2.4j, and that comes up to 9.9j. Now, that describes the vector. This is vector c. If we wanted to find the magnitude, we would have to use Pythagorean theorem. That would just tell us how long the vector is. And it would be 2.2 squared plus 9.9 squared. That would give us the magnitude. And if we wanted to find what the angle that it made with the positive x-axis, we would use the inverse tangent of the y component, with j component, over the x component. And this is in the second quadrant, so we have to add 180 degrees to get our final answer in magnitude and direction. These two are equivalent. They're the same vector. Be careful if I ask, or a question on the test asks for what is the magnitude, you need to do this process here. And if it asks what's its direction, you have to do this process. If it's just asking for what is the vector, this is perfectly correct. Next up, here's your multiple choice question. Now, I mentioned how do you convert your unit vectors to a magnitude and direction in 2 dimensions. This is what you would do in 3 dimensions. It looks like Pythagoras. It's the sum of the squares of the components. Take the square root of that sum. The angle is a little bit more challenging, and it depends upon what coordinate system you want to report the angle in. So usually in 3 dimensions we're not going to ask for an angle, which is good for you because calculating the angles is usually a pretty significant exercise in trig and algebra. So we're going to go with the idea that the unit vector notation fully describes any vector that we're interested in. Now, here's your free response question. See you tomorrow.